everyone's dishes.
Each bring dessert.
Oh, that'll be the last time Chef Pierre comes in. All right.
Well, for Pie Day.
For
How was
pie
it for
day.
last
That would
Tuesday
actually be
for,
such a good idea.
Chef Pierre?
Who won again? Was it Grant won again?
Yeah, I'm so
It's
biased.
so biased.
This has to
Yeah,
be
Not biased.
There needs to be an independent investigation into this guy.
Yeah.
He needs to be blindfolded.
He needs like a control
I'm
group.
serious. I know you need a blind study.
Because you can't go back on your grade after you've already graded it and moved on.
You're trying to.
Hey, talk to Chef Pierre.
An
I'm not Chef
investigation
Pierre.
needs to happen.
I'm not Chef Pierre. Talk to him.
Chef here, the cordon bleu chef.
Yes.
All right.
We're in good
Um,
contact.
So, in chapter 10, we're going to be looking at a new distribution. You know how we had Z distributions and T distributions? We got another distribution, a new distribution.
No way.
What's the letter?
What's this one?
You won't guess. You would never be able to guess this one.
It's not even a letter.
It's
like
alpha
Alpha test.
distribution.
You're getting warmer there.
Oh my god.
No?
Beta
No.
distribution.
Did you grade those quizzes last night?
Almost. They're almost done. I'll give back to you. The distribution that we will be using.
What's that?
That's wavelength.
Wavy X.
This is the chi distribution.
No,
That's
not what that
cheese.
That's chi in the Greek language.
says. That says I.
Chi. The chi, and actually it's called the chi-squared distribution. The chi-squared distribution.
Ooh.
It's actually used for things before this chapter. Like we did not study it, but when we did hypothesis testing for sample means, you could do hypothesis testing for standard deviations. You change the distribution that you use for standard deviations. You actually use the chi-squared distribution rather than the T or Z distributions. It's just another distribution that's used in statistics. So let's talk about goodness of fit. A couple different definitions here. A multinomial experiment. A multinomial experiment is a probability experiment consisting of a fixed number of trials in which there are more than two possible outcomes. Multinomial experiment is a probability experiment consisting of a fixed number of trials in which there are more than two possible outcomes. A chi-square goodness of fit test is used to test whether a frequency distribution fits an expected distribution. So what we're going to be using here is we're going to be running an experiment, basically running a survey, and seeing, and our results are not necessarily just like one or the other, yes or no, success or failure. It is the results can be, come out to be a frequency distribution. Okay, and that's what's called a multinomial experiment, right? When the results can come out to be a distribution of values, right? Where you have, I like to think about it as, how you get those surveys where the options are strongly agree, neither, strongly disagree, or whatever. You know what I mean? You have like 5 options. Well, when you get your data out of those surveys, it comes up in like a frequency table where like this many people chose strongly agree, and this many people chose somewhat agree, and this, so it comes out as like a frequency table. And there's expectation of what we believe is going to come out, but then there's actual observed values that we see that it comes out to be. And the chi-square goodness of fit test is used to test whether a frequency distribution that we observe, that we study, is actually a true fit to the expected distribution. Okay? Because what we're going to have is an expected value, one that we believe is going to happen based on some sort of prior knowledge about our population. And then we run a frequency distribution and we say, okay, these are your options. Tell me what where you fall in. Find our frequency distribution and say, okay, now we're going to be using this chi-square goodness of fit test to say, is that frequency distribution a true representation of our population? And again, that chi-square is just the, it's kind of like it's just an X, but the left side of the X is just a little bit more squiggly than the other. and it's chi-squared. And that symbol is just the Greek letter chi. C-H-I, chi. It's funny, when I got to college and like started seeing all like the fraternities and sororities, like I, being a math person, like had seen all of these symbols before, and it's like, why are you guys using math symbols as your like fraternity letters?
They just love that.
You know, because there was a what was it? Forget what the fraternity was. Oh yeah, it was Sigma Epsilon. Sigma Epsilon, and it's like sum of epsilon. Like, what are you trying to say on the front of your head? Me being the nerd. For example, assume that I think that if LHS students were asked who their favorite math teacher is, they would say, and I just threw these numbers in there. I should have made myself way higher, but maybe this is the distribution that we believe is going to happen, right? For example, assume that I think if LHS students were asked who their favorite math teacher is, they would say 30% of students would say Mrs. Wolf, 20% would say Ms. Napolds, 15% would say Mr. Delap, 25% would say myself, and 10%, why is Westfall so low? What do I got against him? Now, this would be our null hypothesis. The distribution itself is the null hypothesis. When we run a hypothesis test, I would say my null hypothesis, and this is how I write it every time. The book writes it just a little bit different. They like write out the distribution every single time. I say the null distribution, the null hypothesis as the distribution is as shown. And just within the work, make sure that you show the frequency distribution that you believe is going to happen. That means the alternative hypothesis is that the distribution is not as shown, right? Because if this is the equal to, well, then the alternative hypothesis would be in the not equal to, right? But the alternative hypothesis would be the not equal to. The distribution is not as shown, right? Copy paste, put the word not in there. So this would be our null hypothesis. And the alternative would be that the distribution differs from the claim. The claim is generally the null hypothesis with the goodness of fit test. Okay? And that's where the name comes from. With how good does this fit the actual data that we believe to come out? Okay. So now that we have our percentages, what we expect to see, right? We expect to see those percentages come out. So what happens if we go and actually conduct a survey? Well, then there's going to be an observed frequency, right? One that we actually test out. The observed frequency, we're going to be using the capital letter O. The observed frequency of a category is the frequency for the category observed in the sample data. So we run a frequency distribution, and we say that out of, I forget what number I use, I think 500 people that we survey, out of 500 people that we survey, 75 people said Mr. Lavin. Right? That is the O value for my category. The expected frequency is the percentage applied to the number of my sample size. Like, for example, if I chose 500 people, and I knew that I was supposed to get, or I believed I would get, 25% or whatever that was, how much of those 500 would be my 25%? You just go in, you find 25% of 100, or 500, whatever it may be. That's your E value. That's your expected frequency. The expected frequency of a category is the calculated frequency of the category. That's kind of like the relative frequency, that we did all the way back in chapter 2, the relative frequency of the data. Expected frequencies are obtained assuming that the hypothesized distribution is true. The expected frequency for the I know, like this is how they put it. The ith category is the expected frequency, E sub I, is equivalent to N, the number of people that you're choosing to survey, times the percentage, P sub I. where P is the assumed probability of that category. So again, if I wanted to calculate my expected frequency, I would say, well, or like the Mrs. Wolf's expected frequency, it would be 30% of the amount of people that I'm going to survey. And that's the expected frequency. I compare that against my O, my observed frequency, and we can run some numbers based off of that. So again, we have these two things, observed frequency and expected frequency. Again, observed frequency is the one that I have actually run, right? The one that I have said, okay, I'm gonna survey 1,000 people, 500 of them said this. That's my observed frequency. The expected frequency is always based on your null hypothesis distribution, the one that we believe to be true. The one that we believe to be true. And then we say, okay, how closely does that actually fit the data? Okay, so let's take a look at that. Now, assume that I actually sample 500 random students with these frequencies. And 120 of them said Mrs. Wolf, 75 of them said Ms. Apples, 100 of them said Mr. Gillette, 140 of them said Mr. Laverick, and 65 of them said Mr. Westfall. Find the observed frequencies and the expected frequencies. Find the observed frequencies and then find the expected frequencies. Now, I'm going to pull this up just a hair. Actually, you know what? I am going to... Nope, I can make it right there. We're going to find the observed frequencies and the expected frequencies. And this is what you need to do in your homework. Give me tables of your observed and your expected. Okay. Now, the observed frequencies are what we see. Let's calculate. That's not a pen. Let's calculate the expected frequencies. Let's calculate the expected frequencies. And then I'll compare that against my observed frequencies. Okay, so if 30% was believed to be Mrs. Wolf, well, then I'm just going to take 30%, 0.3 times 500, which was 150. I expect 150. How does that compare to actually how many came out? 120. All right, for Mrs. Napoltz, it would have been 20%, so 0.2 times 500, which is 100. How does that compare? Okay, 75 below. Oops. A little bit below. 15%. Hating on D-Lab a little bit too. He's got a low percentage in here. 75. We expect to see 75. How many? 100. Got more votes than expected. 25% of 500. 125. Oh, I overperformed. And then 10%, so 50. And 65, also overperformed. So we see a difference between what we expect to see and what we actually observe. So how do we say, is that a good enough fit for the data? Is this distribution a true good model for the overall population? So what we can do here is run the chi-square goodness of fit test. Here are the conditions for it. First thing is the sample must be random. It must be a true randomized sample. Second thing, each expected frequency must be greater than or equal to 5. Each expected frequency must be greater than or equal to 5. Okay, basically this second piece here, make sure that there is a big sample size. Okay, because that's kind of the thing that was the sticking point for the t-distribution as well, right? It had to be random and it had to be a big sample. Same thing is true here for this frequency. Each expected frequency, each overall value that I expect to see come out must be greater than or equal to at least 5. So on the bigger side of the sample size, and the sample that is chosen must be random. So those are the conditions. If we meet the conditions, then we can use this chi-square distribution. So how do we find our test statistic? How do we compare? Well, here's the formula for the chi-square distribution. If the given conditions are met, then the sampling distribution for the goodness of fit test is approximated by a chi-square distribution with k minus 1 degrees of freedom. What is k? K is the number of categories. I don't know whether you just call it C. Okay. K is the number of categories. K minus 1 degrees of freedom. And the test statistic is chi-square is the sum of O minus E squared. So the difference from what you got from your observed and expected squared divided by your expected. Observed minus expected squared over expected, where O represents the observed frequency of each category and E represents the expected frequency of each category. I've got to get you your chi-square table too. Let me do that to you real quick. And again, these will be given to you on any quiz or test. Have these handy when you're doing your homework. Merry Christmas. You're welcome. There you go. Now, again, the chi-square distribution is not just used for goodness of fit. It's used for a lot of different things. Okay? It's used for a lot of different things. And again, one of the other things it's used for is standard deviation. When you're using hypothesis testing for standard deviation, which we don't get into, but you can use that same distribution, the chi-square distribution. But for our purposes here, we're going to stick to this. Chi-squared is equal to the sum of O minus E squared over E. And that's going to be different for each category, right? As I change the category, that's going to different. Each category is going to have its own observed and expected. So you're going to find observed minus expected, you square it, you divide it by the expected, and then you sum them all up. When you sum them all up, that's going to be your test statistic. So looking at your table here, we have your degrees of freedom along the left side. We also have our alpha across the top. So I'll be giving you a level of confidence. Okay, I'll be giving you a level of confidence. And that will change what the rejection region may be. Now, think about this. Because I square O minus E, even if it's an under approximation or an over approximation, if the expected value is an over approximation or an under approximation, no matter what, it's going to get squared. That means it's always going to be positive, right? This value is always going to be positive. Even if E minus O is small, that means chi-squared is going to be small, not negative. As the differences get larger and larger and larger, chi-squared gets larger and larger and larger. So this is always going to be a right-tailed distribution. I'm never going to look at a left-tailed distribution here. It's always going to be a right-tailed distribution because as I increase the difference away between my expected and my observed, chi-squared is also going to just keep getting bigger and bigger and bigger and bigger. So if I choose to reject, because think about it, if the null hypothesis is my distribution, if the null hypothesis is my distribution, I am going to choose to reject. The only thing I could do is reject that distribution. I'm never going to be able to accept that distribution. I'm just going to be able to fail to reject that distribution. Okay? The claim is the distribution meets the data. So I'm always going to be saying, okay, if I choose to reject that distribution, that means the values of O minus E were too big. The values of the difference between the observed and expected got way too large. Therefore, chi-square is way too large. Therefore, if my chi-squared test statistic comes out to be bigger than the value on the table, then I have to reject my distribution. If chi-squared, my test statistic, comes out to be less than the value of my table, well, then my distribution is okay. Can't really say that in terms of my hypothesis testing. I just have to say, well, I can't throw it out. I can't reject it. I can only just fail to reject it. But it's always going to be right tail. Okay. So let's run a test. Let's run a chi-square test using alpha 0.1. Let's run the chi-square test. Do this with me, because we're only going to do this once. Let's run the chi-square test on that sampling distribution that I have. Okay. Now, I am just going to copy the observed and expected down, and I've lost my notes somewhere along the way. Oh, found them. Here we are. So I'm just going to copy down my data. So I had Wolf, I had Napholtz, I had Mr. Delap, I had me, and I had Westfall. And this is what I expect to see in your assignment, in the homework. Okay, I'm going to make a table here. I always like to put my observed first and then my expected next. Okay, I observed 100, and this is just copying off the previous slides. 100 for Wolf, 75 for Napholtz, 100 for DLAP, 140 for me, and 65 for Westfall. I expected, using that percentage applied to 500, 150, 100, 75, 125, and 50. Now, to run my test statistic, I need to calculate O minus E squared over E. That's what I'm going to calculate for each one of these. And yeah, you have to do it for every single one of your categories. So you find your difference between the two. Now, these ones, it's not too hard to find the difference. So Wolf has a difference of 30. Square it. Divide by 150. Divide by E, not O, by E. 6. Okay, Napholtz has 25 squared divided by 100. 62. 6.25. Okay, DLAP has 25 squared, but now this is divided by 75. 8.3 repeating. Okay, I had a difference of 15. 15 squared, divide by 125, 1.8. And then the 65, that's a difference of 15 squared divided by 50. 4.5. Now, what do you notice about the data that's closer between my observed and expected? They get a smaller value there, right? The smaller the values, the better for your distribution, at least. I guess if you're trying to disprove a distribution, you want bigger values, right? In this column. So I know which one was the furthest off from observed and expected. DLAP, right? We were way wrong on DLAP because that has the biggest difference here as compared to what we expected to see. So now let's add that all up. 6 plus 6.25 plus 8.3 plus 1.8 plus 4.5. 26.85. Okay, that's going to be our test statistic. Let's write out our hypothesis. Let's write out our null and our alternative hypothesis. Now, what is the null hypothesis? It's always exactly the same. The distribution is as shown. If you look at the key for this book, they write it out every single time. That's ridiculous to me. What do they write out? They say these percentages. Okay, they say wolf would have 30%, apples would have 20%, and so on and so on and so on. And they would say, that's my null hypothesis. I am okay if we just say, our null hypothesis is that the distribution is equal to this. The distribution is as shown. That means the alternative hypothesis is the distribution is not as shown. You could say the distribution differs. That's what the book says. The distribution differs from the one. Actually, I think it just says that. The distribution differs. So the distribution is not as shown. Now, again, this is the same type of thing that we had before. The null hypothesis is always the equal to. The alternative hypothesis is the not equal to. Our claim here is that the distribution is shown in the null hypothesis. So the really only thing that we can do is disprove our distribution. Not necessarily say that it's true, but disprove it. Now, what is our rejection region? Let's define the rejection region. Okay, now for this, I need to find my degrees of freedom. How many degrees of freedom do I have? 4, because I have 5 categories and I always subtract 1. 4 degrees of freedom with an alpha of 0.1. So let's look at our tables for 4 degrees of freedom with an alpha 0.1. I see 7.779. 7.779. So if chi-square comes out to be greater than 7.779, then we reject. Okay? Why do I say greater than? Why not less than? Because it's a right-tailed test. So my rejection region is if that chi-square comes out to be greater than 7.779. Does it? Yeah. My sum of the O minus E over E's came out to be 26.85. So 26.85 came out to be greater than 7.779. So therefore, I reject my null. So what am I saying? The distribution is not valid. No good. Throw it out. Start from scratch. Get new percentages. Because that's not a good distribution for your data. That make sense? And again, we are testing the percentage distribution, right? We are not testing our sample. No, we're not testing our sample. We're testing whether those percentages were correct that we started with. That's what we're really using. Okay, that's what we're really testing. We're not testing our sample. We're using our sample to test that, but we're testing whether these percentages were accurate. That's what we're testing. That's the distribution as shown. These percentages. Okay. All right, let's be done for today. Maybe we'll do one more tomorrow. You gonna do one more tomorrow? We'll do one more tomorrow, and then I'll let you work on your homework. Oh, I think I took out 11. But you'll have time to work on that tomorrow. That is not homework due tomorrow. That is homework that you'll probably get done in class tomorrow. All right, I'm gonna turn off the video here.